Hello, everyone. My name is Sumeet Singh. And as Chester mentioned, I'm an ML scientist at Turnitin. A quick introduction of what Turnitin is. So Turnitin is my employer. We are a education technology company. We are a learning outcomes company, but we are known very well. We're mostly known up to this point as a plagiarism detection company, but that's not all we do. We also help students learn, and so we are kind of rebranding ourselves as a learning outcomes company. There is a portion of Turnitin called Gradescope, which we acquired in 2018, and that company helps in the grading process. And so again, Turnitin is learning outcomes company. We also and it's education technology company in general. I specifically so far, or this project that I'm going to share with you is a Gradescope is deployed in the Gradescope product. Okay. All right. So I think this will be like a 40-minute presentation. So it's 12:08 now. I aim to finish by 12:50 or 12:45, and then we can have questions after that. So this is the outline. I'm going to describe the problem and then a history of the neural network approaches to handwriting recognition, and then finally our solution. And the reason for this tour of history of neural HDR is so that it's going to show how we started with very basic digit recognition, and how the community developed more and more capabilities. And finally, our solution is a very logical evolution of the previous solutions that have been there. So I'll just link it up all the way from the start of single digit recognition all the way to full page. So as I just mentioned briefly, Gradescope is a product of Turnitin. And what we do is we help instructors grade their test submissions. And there's a lot of AI involved in that, a lot of computer vision for automatically extracting answers from scanned pages, because most of the submissions so far have been scanned pages. So they are handwritten, the answers are handwritten, and then they are scanned, or maybe photographs, digital photos, and then they're uploaded. So as part of that, a lot of computer vision happens, and handwriting recognition is part of that. Specifically, we have a category of answers of questions called short answer questions or short answer submissions, which which involve free text. And so that's like one of the use cases for this handwriting recognition, amongst others. So the problem description. So first, I want to establish what is full page handwriting recognition. Typically, if you look at academia and you look at papers and you look at a lot of body of work that's been done so far, handwriting recognition is mentioned, and usually handwriting recognition is portrayed as being single word, or maybe like multiple or single line recognition. And the typical data sets that you see look like this, at least in academia. I'm sure in production and where in companies where they have to deploy real world use cases, they would have different data sets. But this is the kind of data set that you will see in academia, and the papers and the different models are compared against these kind of data sets. So this is one form or one paragraph, and very cleanly separable lines. It is called IAM data set. So the horizontal lines are all neatly separable. They are text, and same handwriting, and the text extends from the left boundary all the way to the right side. So most of the work in academia makes these assumptions that the text extends all the way from the left edge to the right edge, and there's nothing in between. This is the kind of stuff that we deal with in reality. And so many answers are full page, many answers are 1/3 of a page. So, they range. And most of the answers are actually not full page. They are about 1/3 page, but we also have full page answers. And so this is one example of, I think it's Python code, and different kind of symbols. There's crossed out text that's supposed to be not transcribed, and then there's indentation. So indentation is also important in many use cases, as you know, in Python. So that's one example. This is another example. So here again, this is full page, but the actual amount of text is limited here. And I don't know if you guys can see my cursor. Can you guys see the cursor? The pointer arrow that I'm moving about?
Yes, yeah, we can see it.
Okay, nice. And then there are some drawings here which should not be transcribed, and there is some associated text here that should not be transcribed. So, these are the kinds of use cases that we face. Again, there's another one here, and you will see there is some mathematics embedded here, like pi bond here and pi bond here. There's a lot of mathematics embedded here, and there is some inline math here as well. Whereas in this case, there is a side note here, which actually is all math. So in one of our use cases, we just want to completely omit all the math. We just want to skip it. And we would only be interested in transcribing this part. Oh yeah, so the other thing I forgot to mention is that typically a scanned image would look like this. And what you see here neatly, black over white, that is image binarization. And so there's a lot of computer vision that goes on to convert from this kind of grayscale image to a black and white image like this. And I'm not going to delve into that today, because today is mostly about, it's just about the handwriting recognition part. More examples. So basically, since there is so much variety of different types of text that we have to deal with, and as opposed to very neatly separated paragraphs, separated lines. So then we came up with a formulation of the problem, and the way that we formulate this problem is that there are different regions on the image, and we classify them as text and drawing and math and tables, etc. And so this is one text region. This is another text region, and then this is math. So again, in our use cases, we do one of two things. One is that we transcribe only the text regions, and we transcribe them in the order in which they are supposed to be read. So, this region first, and then this is the next region. And we would completely skip this part, okay? Another mode is where you will recognize this part, but you will only emit like a math token here. So it's just a tag. It's like an HTML tag. It just says math, and that's it. So it'll identify the region, excuse me, but it's going to not transcribe it otherwise. So there are these two different modes in which we do train the model. Okay, so it's basically just stating formally the problem. The problem is to implicitly identify regions that should be transcribed and regions that should not be. So, drawings, scratched out text, some unrecognizable symbols, tables, and math should not be transcribed. So, the model has to recognize the difference and then correctly transcribe the text regions in the order or in sequence that they were intended to be read. So that's like another thing that the model has to implicitly learn. And then perform auxiliary tasks. So for example, I mentioned over here that an auxiliary task could be that emit identification tokens for math, drawing, and some other such untranscribed regions. And then maybe emit end of region markers, meaning that the region separators. So that definitely emit end of line markers, also emit, for example, indentations. So those kinds of things. So in an indentation, I showed you one example with Python code. So that kind of stuff. Now, with typical HDR or typical handwriting recognition that you will see in academia, the only thing they're interested in is actually just the text. They do not care about the indentation. They don't care about line breaks. So that actually becomes a problem for us, because in many cases, your regions are overlapping. And so I'll give you one example. OK, I'll have to go later. So for example, take two-column text. In two-column text, you have one column here, and then you have another column here. And what happens in that case is most of the models that we've seen, even in production, they will, our model will actually transcribe the left column first completely, and then the right column. Whereas with the typical models that are out there in production, what you will see is that it will transcribe line by line. So if there are two columns, then it'll take the first line of the left column and then the first line of the right column, and it'll join the two together. And then it'll go on to the next one. So that like totally just merges the two columns, and that's not what we want. So that's why it goes beyond just full paragraph handwritten text recognition. So now I'm just going to go through the history of neural networks. And so if there are like any, maybe if I can take a minute here, if there are any kind of blazing questions that were not clear about this portion, then maybe you can spend a minute. Chester, is that okay, or should we just?
Yeah, that's fine. I mean, just everybody, we got plenty of time.
Okay.
So if you have questions, you can directly type the on the chat area, or somehow raise the hand. If I can see raise the hand, and then I unmute you, or somehow I don't know how to do that yet. But if you can just type your questions.
Okay. So yes, the question is, there's a question: is your goal to introduce math and graphs, or do you want to skip it? So right now we want to skip it, but we have done prior work where I've done prior work where I transcribe math, and so that will be like a second kind of phase where we will basically start tackling math and tables. But in this one, you're right, we're going to skip it. It's just going to be text. Okay, so I think I'll move on, and because we'll have time at the end for more questions. Okay, so the first paper that I want to introduce is Jan LeCun's 1998 paper on isolated digit recognition. So this was a seminal work at that time. I think it started the deep learning revolution, although it didn't quite start in 1998. It took some time for it to gather steam, but this is like one of the seminal works. And so, a CNN classifier, but it needs character level segmentation. So they deployed it for recognizing numbers in checks. So in handwritten checks, you know precisely exactly where the number should go. So they employed it there, but it was still a single character recognizer. And in order to recognize the full string of characters written by hand, numbers, they applied some heuristics, which I kind of won't get into, but it's called, they called it graph transformer network for recognizing words. By words, I mean, if you have like 368.10, so, how you recognize the full string, if you're not given isolated digits. So this work mostly concerned about by some way you segment out, you isolate the digits separately, and then you give them to a CNN. And they were not just isolated, they were also size normalized. So a lot of heuristics, which was completely data dependent, which was applied before the CNN classifier was ready to do its job. So that was like the first one. And then, as an evolution, this is a 2008 paper from Alex Graves. He did a lot of work on handwriting recognition, and it's actually part of his PhD thesis. So this specific work employs LSTMs. It does not employ CNNs. It was employed to recognize Tunisian town names in Arabic, and they won that competition at that time, although none of the authors actually knew Arabic. So again, seminal work, and this basic architecture was, in fact, I believe even today it's probably the state of art. Like most people are using this even today. And the basic idea is that you encode or embed the image using multi-dimensional, so 4-directional LSTM cells, and then you keep average pooling or with the feed-forward layer, such that at the end you collapse the vertical dimension, so that at the end you just have a single sequence of embedding vectors. So in this case, it's 121 embedding vectors. So the implicit assumption in this model is that you are only dealing with a single line of text. You're not dealing with multiple lines like a paragraph, and you're definitely not dealing with multiple paragraphs. So that's just not it. So that this assumption is just baked in. And so that's like, but this again, so that's one. The other thing is that, as you can see, that regardless, so whatever the size of this image, once you do the subsampling, ultimately you will come to you'll come up to some sequence length, which is a fraction, a fixed fraction of the length of this image, the number of pixels in the width of this image. So, which may be unrelated to the actual number of characters in the sentence or in the word. So how do you deal with that? And in order to deal with that, Alex Graves came up with the CTC idea, which essentially draws a graph of a very complex acyclic graph of all possible words that might be predicted by this model, because at the end, what you get is probabilities over the entire vocabulary. So, if your vocabulary here is 100 or 200 or whatever, you will, for every step here, so you get 121 distributions over those 200 symbols. And then you have to figure out, you have to pick for each step which one. And actually, there won't be 121, there's just going to be 5. So those 121 have to be compressed into 5. So for that, he came with CTC, which basically goes into the space of all possible combinations and finds out the most promising ones. And that's pretty complex. And it's quite expensive compared to the other methods that we came up with, that community came up with later. The next models were almost exactly the same that I just showed you, but with just slightly some different tweaks, but single line recognizers. So same as the one I showed you, and this specific one over here, Pham et al. It's 2013. So they added dropout, and they also tried it on bigger networks, and they made some small changes to the block sizes and kernel sizes, etc. But essentially the same architecture. And here again, you have to have single horizontal isolated lines, which means that you have to have another process, computer vision process before this, that will take your image and it's going to split it into individual lines. And those processes, those systems are usually, they have a lot of heuristics involved in them. And those heuristics are obviously handcrafted. I mean, the algorithm is handcrafted. The heuristics are very much dependent on the data. And so if the data changes, which it does in real life, then you have to go back and redesign your segmentation algorithm. And that's like, there's a lot of work. So that's one disadvantage of all the models that require segmentation. In other words, all models that are not full page, unconstrained handwriting recognition models. So all of them, which are, they will either require you to segment out a word or a line or a paragraph. Okay, so yeah, so and the other issue with this architecture is MD-LSTMs. They are sequential, and in this case, you employ 4 of them for 4 directions. So the training is quite slow. So that's, and long distance dependencies tend to get forgotten. So that's like another issue with LSTMs in general or recurrent networks in general. So, they on the IAM data set, they got a 13.92% character error rate without language model and 5.1% with language model. And language model is basically whatever comes out of here. Then again, you constrain the vocabulary, and using a constrained vocabulary of words, which means you have to know in advance what words are going to be in the text. And once you have that, sorry, is there a question or something? Okay. So it's a constrained vocabulary, and once you have the constrained vocabulary, then you can make if there are certain words that don't fit in it, then you can make a guess as to what's the nearest word that might have been in the real text. So that's a language model. We don't use language models because we need to cater to all different kinds of subjects, math, physics, biology, economics, medicine, and different. And each of them comes with their own terminology, especially medical science, for example. There's a lot of terminology there. So, and then proper nouns like people's names of places. So we don't restrict our model to a limited vocabulary. And so I'm mostly going to be comparing with the error rate of language without language model applied. Another similar model, Voigtlander, they rely on deslanting. So basically they take the text, they segment it, and then they deslant it, which means, again, more heuristics applied. And then based on that, they actually, I think, got the best CER, which is 4.8%. But I'm sure if you take some other data set, which is not like IAM, something else, that deslanting is not going to work for that other data set. These models that rely on heuristics are pretty brittle. So Bluch et al. Don't remember when the paper came out, 2016. Okay, 2016, they came up with a model. It was a very good attempt trying to do exactly what we have done, which is no layout assumptions, so multi-paragraph full page recognition. And the portion that you see over here is, excuse me, it's the previous model that we saw in the previous, so this whole part. So that becomes now just an encoder, and they've added a decoder over here, which is an LSTM with a feed-forward layer, and also attention. So this model, basically, the idea was that it could take multiple paragraphs and you could train it on multiple paragraphs, full page, end to end. And it was a very good attempt on the IAM data set. At paragraph level, they got a CER of 16.2%. But apart from the fact that the error rate is not very good, it was too slow. So the authors themselves said that this model is too slow, and so it's not, you can't really deploy it. So later they went they scaled back to a single paragraph recognizer. But a quick note on this one, this attention module here also uses MD-LSTM. So you have like an MD-LSTM working here, and you have multiple layers of MD-LSTMs, and all that has to be back propagated for each and every single step for each character that's being recognized. But one of the good things about this was that it didn't employ CTC, it just employs like regular cross entropy objective function. And it emits an end of sequence symbol, like any sequence to sequence model. So it decouples the size of the input image from the output here, which means that if the image should be really big, but if there's just like a couple of characters in there, this LSTM is only going to run for 2 steps, and that's it. So that's one advantage of this model. So as I mentioned a minute back, because the previous model was too slow to learn and very slow for inferencing, they went back to single paragraph models. And it's, again, pretty similar to the previous one, like this one, except that here they apply the attention on a line-by-line basis and not on a step-by-step basis, which means that they make the assumption that the image has lines extending from the left side all the way to the right side, which means it won't work for these kind of scenarios, because here the line, if you start from here, and you assume that this whole thing is one line, then you obviously got it wrong, because this is a 2-column format. And similarly, you can have multiple regions, not just 2 columns. So that's a problem with this model and with this approach. So what they require is that, excuse me. So what they do require is that there should the paragraph should be isolated and segmented. So again, you have to apply some heuristics and another method to separate the paragraph out. And after that, the paragraphs are individually recognized, and then they are just stitched together. And similar thing happens with lines here as well in this model. So indentation is like lost completely. So if there was indentation, you just wouldn't have it, because the model just assumes a line is a line. And so it's going to predict as many lines as there are in a paragraph, and it's just going to stitch them using a single new line character, and that's it. So if you had an empty line in the middle, that wouldn't actually get reproduced, or if you have indentations, that wouldn't get reproduced either. Okay, then next is towards, so there's the next trend that kept happening was towards more parallel architectures. So up till now, we looked at LSTMs or MD LSTMs, which are all recurrent, and so they are linear and it takes time to train them. Whereas if you go with CNNs or transformers, then at least during training, transformers are parallelizable, and CNNs are parallel during both training and inferencing. So this is again for the same author, Bluch et al., and then Pig-Server. Apologies if I didn't pronounce this properly, but both of them basically have the same. They took the previous architecture and replaced the encoder portion, which was LSTMs earlier, MD LSTMs. They replaced it with CNNs. In this case, it's a gated CNN, and this is just a regular CNN here. And so more parallel architectures, faster to train. However, in this case, it is still a single stack, and which is not decoupled. So you will still run an LSTM that is going to run over the entire length of the image feature map, which means that if your original image is twice the width, then this softmax here, this decoder, is going to come out with twice as many predictions. And then you have to run it through CTC to compress that, like I'd shown before. If you have 121 activations at the end, but you only have 5 characters, then those 121 have to be compressed to 5. And so that's what CTC. So this still has that issue, but it was a step forward in that the community started to get rid of sequential processing in favor of parallel processing, which makes it easier to train much quicker and to deploy. And finally, the last step in the evolution is decoupled architectures, where you don't have the problem that I mentioned earlier about having to rely on CTC, because now you have truly an encoder, a separate encoder and a separate decoder whose lengths are completely decoupled from each other. So the job of the encoder is to encode the image, and the decoder then decides on how many steps it wants to decode, independent of the size of the image. So there are 2 architectures here. The one at the top is very bespoke. It's very different than any normal architecture. And but the wonderful thing about this is that it doesn't have any teacher forcing, and I'll get into that a little bit later. But for people who have built or understand sequence-to-sequence models or transformers applied to NLP, you guys already know what teacher forcing is. The good thing about this model here, they call it DAN, is that it has no teacher forcing, so it's all parallel all the way. And they also have a way of decoupling the size of the output text, decoupling that size from the image size. But it's a bit a little bit complex, and they do have like a max size, and then so they do run the decoder for that max size. So that's like a small disadvantage there. But the good thing is it's all done in parallel. It does not emit, I believe. So yeah, maybe both of them do emit an EOS. So that's quite wonderful. This model here, Kang et al. So this one is like a very modern architecture similar to ours, but not the same. So here they have a CNN encoder, ResNet, and then they stack on top, and of course they flatten it. Again, when they flatten it, they basically make the assumption that there is only one line of text in the image, which means again that they are expecting that there's going to be a line segmentation process running before this model kicks in. So that's one disadvantage of both of them. They're single line recognizers. But other than that, this one is a very modern architecture. So they have stacked a transformer on top of a ResNet. And so this is the self-attention part on the image. So that's the transformers encoder portion. And this is the transformers decoder portion, which employs cross-attention on the output of the transformer encoder. And they got 4.7% without language model, which I believe is the best so far. So I think I have mentioned this during my talk. And so I'm just gonna basically, skip this. So now we come to full page HDR. So there is this one paper that deserves mention, which is full page HDR on paper. And they did present results on a full page data set from ICDAR. They presented good results. The only thing is that they also actually make the assumption that the lines stretch from the left side all the way to the right side. So they don't actually deal with multiple paragraphs or two-column text, etc. Now, I think they call their work full page because there was a full page HDR challenge, I think, from ICDAR, International Conference on Document Analysis. So maybe in that context, it's full page, but it's still making assumptions about the text. So it's actually three neural network system. It's pretty complex. And okay, so does someone have a question, Saul, or was that just by accident? Okay, I think that was by accident. Okay, so so this is a three-stage system. There is a start of line detector, and then there is a line follower, and finally there is a single line recognizer. So and then this it requires iterative curriculum. So initially you have to have a little bit of data that actually has bounding boxes, and it has the start of line markers, and then you train the start of line position model first, and like that. So and then there is iterative curriculum learning. So it's very bespoke, and but it won't handle arbitrary layouts again. So their line level CER is 6.4%, which is actually not as good as the state of art, which was 4.7 that I just showed you earlier. So just one note on this model, it's a very good attempt, and I think it's a lot of hard work how they were able to make it work. But I think as a general model for deploying generally, there is it'll be hard for someone else to deploy this, to actually build it and train it, and to get the kind of data that's required. Plus, it doesn't handle arbitrary layouts. So then we come to our model. So this is an evolution of everything that happened before. And one of the good things about this model, other than the fact that it'll handle arbitrary layouts, etc., and it'll deal with formatting and indentation and auxiliary tasks, I think one of the major advantages is that it's a very simple model to implement. And for anyone who actually wants to implement a state-of-art handwriting recognition model, all you need to do is you need to get a ResNet, which is already available in PyTorch, and a transformer, which again is in PyTorch. And then you need data to train this. So most of your work is actually going to be in the data, in acquiring the data and creating the data stream. Other than that, the model itself is really simple, and it uses very simple ideas. So it's an image to sequence model, similar to image to sequence models that have been seen earlier with LSTMs. So the ones earlier with LSTMs usually have an encoder, which is some form of CNN. And then there is a LSTM and attention module, which decodes the image into text or whatever else. And instead of an LSTM, we have used, instead of LSTM plus attention module, we have used a single transformer decoder. So we don't have a single, we don't have the transformer encoder, unlike this model here, which has also a transformer encoder, which makes it larger and slower. We actually don't believe that you need a transformer encoder, although if you did have a transformer encoder, it would probably give you better accuracy, surely. And but we got rid of that because it makes the model too large. So some normal things we did was we added 2D position encoding, and there's line number encoding, which is optional. And you can actually omit that in your model, and it should work almost as well. And so, and then we have local attention inside the transformer stack, inside the transformer layers itself. Usually, transformer has a global attention. We have localized attention. But if you see the paper, we say that we didn't see a lot of difference between applying local attention versus global attention, other than the fact that it trains a little bit faster. And because the GPU memory is a little more fragmented with local attention in the way that we implemented it, we were able to train it with slightly larger batches. So this is the model that we built. And let's say it's layout agnostic, so segmentation is not required. It's multi-region, no layout assumptions. It does generate an end of sequence token, which means the model will tell you when it is done transcribing. So there is, the length of the output sequence is also determined by the model itself. So theoretically, then there is no limit on how long you can run the model for what sequence length. So yeah, I've described this. So yeah, we used a ResNet module for CNN, but it's not the pre-trained one. We start with random weights and we train the model from scratch. And so that's all good. Yeah, we didn't use beam search because it really wasn't helping. So we just do greedy decoding, and it takes about 4.6 seconds on a single CPU thread. So a lot of work that we did was on acquiring the data and on actually augmenting the data. So that's where most of or a lot of the time was spent, and also on applying augmentations and making sure that the training data was IID, so independent and identically distributed across as many dimensions as we could think of. In other words, for example, the size of image, or where the image is placed, where the text is placed inside the image. In the case of synthetic data that we created, the font and the font size. So all these different types of dimensions were just randomly sampled so that it was a uniform distribution on the training side. So we also used, we generate synthetic data from Wikitext with about 300 plus fonts. And we have the IIM data sets. We have our proprietary data sets. And over there also, we augment the data set itself by stitching together lines or words if we have available, and stitching them together and creating handwriting, but synthetically creating handwriting paragraphs. So all that is kind of needed because you really need a lot of data. And we have like, 13,000, 14,000 samples in one case. So that's really not a lot of data. So then we had to resort to these different kinds of techniques to augment the data. Ideally, I would say if you have 100,000 samples, that's what's needed. We ended up with 25,000 or something, or 20,000 or so. So not a whole lot of data. So these are the results. I think I've talked about most of them. So so paragraph level. For comparison between different published models, one has to use a data set that everybody has used. So in this case, it's paragraph level IAM data set. And if you take the models which try to be full page HDR models, unconstrained, multi-paragraph, multi-region like ours, then there is only one model that actually attempts that, and that's Blue's model, which has 16.2%. Ours is 6.3%. Other paragraph level models, which are also evaluated on the IAM paragraph level data set, are the ones listed here, the best ones. But all of these models require the paragraphs to be segmented out separately, and that's why I've put them in a separate category here. But all of these also, we kind of the performance of our model beats all of those as well. And then these are results of single line recognizers, which require images a single line segmented. So here, as I mentioned before, Kang et al. Theirs is the 4.7%, and this is really without language model, and that's I think pretty impressive. I just don't know if that generalizes to different data sets. And we have our own proprietary data set of the type that I showed you at the beginning of this talk, so free-form answers, and that we ran across publicly available APIs, so Microsoft Azure, Google, and MathPix, and AWS, and the best of them was Microsoft, and they came down with a CER of 14.4%. So here, lower is better, by the way. In all of these, lower is better because this is the error rate, and ours is 7.6 on that data set, so better than theirs. Again, not a fair comparison because we trained on our data set, they did not. But when you're doing a build versus buy decision, then you have to see what's available and what you can build, and what we built is clearly better for us. Just for experimentation, if you test the Microsoft model on the Wikitext one column data, the synthetic data, then you get 1.4% error. But if you send them two column data, then you get really horrible 50%, 57% error. And the reason is that they are actually concatenating these lines in the two column data. In the one column data, it's fine. It works pretty well. But for two columns, they just concatenate it. And that's basically shows that that's what models are doing under the covers. And that's one of the big problems that we've tried to solve with ours. The model is not perfect. There are a lot of limitations. One of the main problem is performance really deteriorates with out of distribution data, which means that if, so like recently, actually that's a different model, but I think the same thing would apply to here also. So when the data distribution, when the way that the data is placed, when that changes significantly, then the model's performance for that outlier distribution is pretty poor. And when I say poor, it's like 19% or so. And that's not good, because what that means is that we have to train different models for different data distributions, which is actually typical for neural networks. But it would be nice if one could just do it all in one model. And I think it can be done. We just need more data, and the model itself would have to be much larger. So it can be done, it's just that we haven't done it. But one challenge there is that we would need a lot more data, and that means a lot more manual labor. And I think that's probably not a good idea at this time. So we have to find out some method by which we can either do self-supervised learning or some other way to circumvent this issue. So that's, and there are some ideas here, for example, training separate vision models for different distributions. So that could be one example, and then a more efficient encoder, et cetera, and model compression. So these are just some ideas, but I think that's the talk. And okay, 12:52, I think I went 2 minutes over, sorry about that, but now we can open up to questions.
Thank you, Sumeet, for a thorough discussion on this topic and with all the reviews on the papers. So I think we right now open to questions. I know there's 2 questions on the chat already, but just saying, somebody if want to speak rather than chat, you can raise your hand and somehow I can unmute you and then you can talk. So let's get to the first 2 questions. Is a short answer character error rate of 7.6% good enough for Turnitin customers?
Yeah, so so deep learning in general, as I think most of you guys know, is not perfect. So we use it in an assistive fashion and not in a autonomous fashion. So it's assistive, it's not prescriptive. Now, that said, the 7.67% error or 7.6% error that I shared is for full short answers. But if you fine tune the model for some use cases where we are using it, where you apply it only to fill in the blank kind of answers, there the accuracy is much better. But in general, 7.6%, yeah, it's not good enough. What I would prefer is less than 1%. But I also want to say that 7.6% right now is state of the art. There is no other model which does better than this. So this is the state of art of deep learning. And because it's not perfect, we use it in an assistive fashion. So the grader does have the opportunity, and I think with this is used with human in the loop. So there are ample ways of where the grader has to go and validate the answers that have been grouped together. So over there, so yeah, what I'm trying to say is that there is a human in the loop UI where the instructor or the grader has to go through the answers and validate them. Most of them have been correctly transcribed. Some of them have not been. So there are some false positives, and those then the grader will remove those manually.
Yeah, the second question also coming from Dave. It says, what's image binary method? What's the image binarization method did you use?
Yeah, I'm sorry, I actually don't remember that off the top of my head. But that's part of the Gradescope pipeline, which applies to various different models. So, but the model that we have, so for example, the model doesn't require binarization. The IAM data set that I shared with you is not binarized. And the results that I've presented, the 6.3% error rate on the full paragraphs, that is for with unbinarized IAM samples. So binarization is not a requirement for this model. And it's definitely, we didn't binarize the IAM data set.
Okay, the next question coming from Sean. They basically saying, can you use the clear text, the areas which is clear to learn, and then you apply to the part which is unclear?
So this is an image to sequence model. It's a generic image to sequence. So you give it an image, and then it produces a sequence. The sequence can be anything. So if you can formulate your problem in this way, that maybe your output sequence that you're training, it's a supervised training. So the output sequence, if that can have, let's say, some markup, which denotes something, some semantic markup, And if you can have enough samples, then I mean, I would encourage you to try to train the model for that, as long as there is enough signal in the data to make the prediction. So let me just read this one more time. Would it be possible to train the model on the clearest portion of each text to learn the writing style to improve accuracy in less clear areas? So I believe the model is probably already doing that implicitly, because we didn't train the model on one handwriting, right? It's trained on a variety of handwritings and even on text at the same time. So the model is implicitly doing something where it's able to recognize different handwriting. So I don't know exactly what it's doing. It's, as you know, deep learning right now, interpretability is not the best thing that you can do with a neural network, but it could be doing that kind of thing implicitly.
Okay, Dave, I have more questions. Do you do the inference on GPU or CPUs?
So inferencing is on CPUs because it's on Lambda, actually, AWS Lambda. So it's on CPUs.
I see.
Training is on GPUs.
And then he also had, do you have training on the FP32 or pfloat 16?
Yeah. So initially we started with 32, and then we switched to mixed precision training. So the weights during training are kept in 32 bits, but the gradients are 16-bit. And then you take 16-bit gradients and you apply them on 32-bit weights.
Got it. Any other questions? You can continue. As I said, you can either raise your hand and I unmute you somehow or post in the chat. Okay, going in once, going in twice. Okay, all right. So I think that's probably all the questions. Thank you so much, Sumeet. And this is a great talk, and it gave us a great detail. Oh, there we get somebody. Oh no, just say thank you.
Thank you.
Yeah, thank you very much. We would like to thank our partner Bill from the AI Camp to help us providing the Zooms. And we of course thank you everybody to attend from all around the world for this event. Thank you, Sumeet. Okay, we'll see you next time. Okay, bye-bye.